Did you know that light can have a huge impact on our body and health? Not only does it influence when and how well we sleep, but it can also affect our mood, alertness, and even our behavior. Welcome to Light O'Clock! In this podcast, we unpack the science behind body clocks and how light influences our daily biological rhythms. In each episode, we chat to experts in the field and have them break down the scientific topics so you can be enlightened. Today on the podcast, we're asking the question, how does light make us see the world around us? And we're joined by Maydel Fernandez-Alonso. Maydel is a postdoctoral researcher at the Max Planck Institute for Biological Cybernetics in Tübingen, Germany. Here, she investigates how different properties of light influence our circadian rhythms. Maydel, welcome to the show.
Thank you, Caro, for having me.
So, in the last episode, we emphasized the importance of understanding different sources of light that we encounter in our daily lives and how these can influence our rhythms and our biological clock. Now, before we delve deeper into these topics, I thought it would be very good to define a little bit in more depth what we actually mean by light. I think we mentioned the word wavelength, but I don't think that's super clear for the listeners. So maybe we could explain what that means a little bit.
So I guess we can start by defining what light is. So light refers to electromagnetic radiation that is visible to the human eye. So it's approximately between 400 nanometers and 700 nanometers. Beyond, so longer wavelengths are infrared radiation. People might have heard of that. And shorter wavelengths are ultraviolet radiation, which the sun contains a lot of, for example. As a form of wave, of course, light has a wavelength. So this means it refers to the distance between the different peaks of the wave. The shorter the wavelength, so the shorter the distance, the more energy the wave contains. So shorter wavelengths, so people would think of, like, for example, blue light, have more energy than longer wavelengths. Yeah, and another very important property of light is intensity. So when we talk about the spectrum of light, for example, this is measuring for a light source what the different wavelength it contains, but also what is the intensity at each wavelength. And this determines a lot of how we will perceive that light source.
So we go from like bluish colors towards like what is the other end of the spectrum?
The red color. So I guess people would think of the rainbow, for example. That is how light is scattered in the different components of the light. And the color at the end is just the way we perceive them, thanks to our the photoreceptors we have. But perhaps we can start a little bit about the journey light takes from the environment into our eye.
Yeah, for sure. Regardless of what kind of light we're exposed to, at some point, light will hit the eye and travel through the eye to get to different places in our brains, including this little grain of rice that we described in the last episode, which is the biological master clock, the suprachiasmatic nucleus. So I think the aim of this episode is really to describe this journey of light. Yeah, let's just start from the very beginning, right? When I say hit the eye, what part of the eye does it hit actually?
So the most outer external part of the eye is the cornea. And that is like you can imagine like a special kind of lens that protrudes out of the eye. So the eye is not completely round. It has this sort of, the cornea kind of slightly comes out of it. And that's because it functions as a lens. So the cornea is very powerful for bending the light. If you think the first problem the eye has to solve is that the world is very big, right? And the back of our eye is very, very tiny. So it needs to bend the light quite a lot. The cornea, you can think of it like very powerful to bend the light into the eye. And also serves the function of filtering out part of the ultraviolet radiation. So light below 360 nanometers, it doesn't travel into the eye thanks to the cornea. And that's quite important because we talk about how shorter wavelengths have more energy. This higher energy, it means it can damage the tissues. So it's in a way to protect the eye and the tissue inside the eye from ultraviolet radiation. After the cornea, then we have the pupil. So the pupil is basically the entrance into the eye. We see it, you can see the little black dot that everyone has in their eyes. And it's quite important in determining the amount of light that enters into the eye. So for example, at night, our pupils become quite big because it needs to let more light in order for us to see. But then we go outside and the pupil constricts. This means it becomes really small to try to reduce the amount of light to, again, protect the eye. And because we don't need that much light to see outside. Around the pupil, there is the iris. So a lot of people can think this is what determines your eye color. The color of the iris depends on the pigment. So some people have more pigment, then you have darker irises, and then less pigment, lighter irises. People with lighter irises, their image, because they have less pigment, is more transparent to light in a way, so it lets more light in. So people with lighter color eyes, for example, can be more sensitive to glare from being outside in the sunlight. And then after the pupil, there is the crystalline lens. So this is a flexible lens we have inside our eye. So I talk about how the cornea was a lens, but the cornea is fixed, right? It doesn't change shape. So how are you able to see at 2 meters versus 30 centimeters from your face if you don't have, for most people that don't need spectacles to see. So basically our eye is constantly changing focus, the point of focus. Essentially what distance is bringing into focus the objects for. So if you put your finger in front of your face, you can focus on that and then the background becomes quite blurry, right? But then you can very quickly shift to the back and focus at 2 meters behind, and then your finger becomes very blurry. This is because of the crystalline lens. So the crystalline lens is very flexible. You can think of like a balloon filled with water, and it's suspended in some tendons, so like some very flexible fibers. When we need to focus at near distances, the fibers relax and the lens becomes more round. So it bends the light more because it's thicker.
So the balloon gets filled in.
Yeah. Well, the balloon just gets round, whether when you want to accommodate farther, so focus for a far away distance, then the fibers tense and then the balloon becomes very flat.
Okay.
Because it's stretched, right? And then the lens is basically mean the lens is bending the light less, so you can focus at farther distances. And this happens very seamlessly, right? We don't notice that our eyes doing all of this when we try to look at different distances. And the crystalline lens also serves to protect us from ultraviolet radiation because it filters out light below 400 nanometers. And actually, as we age, this lens changes quite a lot. First, it becomes more yellow. So this means that it lets even less shorter wavelength light through. And then also it becomes harder, unfortunately. So this means that older people tend to start needing spectacles at some point because the lens can no longer change shape so easily because it's becoming less flexible. It's becoming harder. So this is called presbyopia, and often that is why commonly people after 45, 50 years old start needing spectacles to be able to see at different distances.
Is that why my mom, when she looks at the phone, she has to keep adjusting the distance of the phone to her head because she cannot see it?
Yes, exactly. So of course there could be a combination of different needs for spectacle, like myopia, but it's very common at an older age that you can no longer focus at different distances. So your eyes, instead of having this ability to change focus constantly, it becomes kind of fixed. And for you to be able to see at different distances, you need something like bifocals or some type of correction like this.
The last thing we mentioned was the crystalline lens, right?
Yeah.
Once the light sort of gets there, how is it processed further down the eye?
Yeah, so the eye is filled with liquid. So behind the lens, it just keeps traveling throughout the eye and then until it hits the retina. So the retina is a layer of tissue that is in the back of our eye and is actually part of the nervous system. It means it's composed by neurons and is basically what grants us our ability to see, right? So the first cells that light hits are actually not the cells that can perceive light. So those we call photoreceptors, and those are actually in the back of the retina. So behind all the other cells that the retina is composed of. But light can still make it through all these other layers and hit the photoreceptors, and that's where light is captured. So these are cells, they're very special because they have the ability to capture photons. And once they have captured enough, they send a signal to the rest of the layers of the retina. So the other 2 layers, they are more in charge of doing some processing to the light that is perceived. So of course, then you perceive the photons and then just a signal gets sent, but then from that to build some type of perception of an image, then you need to start doing some processing, and a lot of that happens in the retina.
So are they scattered around the retina? Where are they located?
So yeah, the photoreceptors have very different distribution depending on the types. So we have two fundamental types. We have the cones and the rods. And then, of course, there are the IPRGCs, which are a special type that you might have talked about already in this podcast. But yeah, the ones we have for a long time known about are the cones and the rods. The cones are further divided into three types. So depending on which wavelengths they are specialized to capture. So we have the red, green, and blue types. And then according to their name, the blue type captures more shorter wavelengths. The green type captures middle wavelengths, and the red type captures longer wavelengths. They are distributed very differently in the retina. So our retina by itself has, let's say, two main parts or two distinct areas. So one is the very center of the retina, which we call the fovea. And this is where our best vision is. We have at least our highest resolution vision. So here we see a lot of detail. And if you're reading, you can think, of course, you would turn the center of your eyes towards the text, right? Because this is where your best vision is. Whether if you put the text on your periphery, you don't see as well because the resolution there is not as good. In the fovea, actually, the fact that we see, the reason we see so well is because the cells are very tightly packed together. So basically, you can imagine these photoreceptors are very squeezed, and then you can have a lot of them in a tiny space. And thanks to that, we can see a lot. And also because all the cells we talk about that are layers that come before the photoreceptors, in the fovea, they kind of move away and they create this indentation. So light hits the photoreceptors directly instead of having to pass through these other layers. And then there, of course, light is captured more efficiently. And then we have the periphery. So in the fovea, we exclusively have cones. And in the very center of the fovea, we only have the red and green type, actually. The blue type is more common in the more outside part of the fovea and in the periphery, of course. The reason for that is because of an optical aberration the eye has, which means that different wavelengths get refracted or bent or focused into different points of the retina. So if you imagine somehow the eye can also be a little bit of a prism, that it separates light scatter according to its wavelength. So blue light, unfortunately, is a bit blurry when it reaches the retina compared to the other wavelengths. So that's why in the very center, because we want to have the best vision there, then there are no short wavelength cones. And then in the periphery, we have a lot of rods. There are a lot more rods than cones. Rods are different than cones. They are specialized at night vision. So they are very good at capturing photons at very low light levels. So they can capture very little amount of light. So that's why they are very useful at night. But then during the day, they become what we call saturated. So it means that they cannot respond so well in high light levels. So during the day, we're normally using our cone vision, and then at night, we normally use our rods to see.
Okay, so we've traveled through the eye, we got to the retina, we've got these super special cells in the retina that enable us to see, I guess, different wavelengths at this point, right?
Well, we're not really able to see wavelengths, but we can at least distinguish different parts of the spectrum. So the short wavelengths, they can perceive light mostly at short wavelengths, but they would still react a little bit to middle wavelengths, for example. So the way we see color actually is that the eye compares the input between the three. So for example, you can imagine for a green cone, for example, that still reacts a little bit to red light because the response is what we call broadband. It means it's not just to a single wavelength, it's to a series of, to a range within the spectrum. How could it distinguish on its own, right, between a very bright red light or a dim green light? It's not possible. And the cell itself that has no way to distinguish. So what the eye does is very clever, and it compares between the two. So now if I have also a red cone, for example, I can say, okay, this is actually a very bright red light because the red cones are responding a lot. If it was a dim green light, it wouldn't so much. So this is how we see color. And we have two main channels on which these comparisons are performed to see color. One is red-green. So there we compare the input between the red and the green cones. And then we have the blue-yellow channel. So we compare the input between the blue cones to the other two. And this is why we call yellow, right? Because it's the combination of red and green.
Yeah. So now we describe sort of how we see colors, or how we have different types of specialized cones that respond to different inputs from the light that we see, right? What about when we see black and white? How does that work?
So in these color channels that I was talking about, because you have to compare one from the other and kind of subtract in a way, the details that we can see are actually not that good, because to see very good spatial detail, you actually want to be able to sum, right, the input from all the cones. So that's what our achromatic channel does. And this is a channel that specializes on seeing very high detail. So if you imagine you're looking at a scene and all these sharp edges and like very fine details that you can see, this is thanks to our achromatic channel. And then the color information kind of gets put on top of this channel in a way in our perception. But because on its own, just the color channels wouldn't be able to have this high spatial detail. And this channel is responsible for a lot of our perception. So, or for example, our perception of brightness, of what is bright, what is dark. Of course, our ability to read, for example, very fine text, very small text in a page. This is thanks to this channel.
Okay. So let's say that we have these cells in the retina that respond to light. And now we described, the different types of cones, and then also these achromatic channels that make us see things in very, very much detail. But for now, these cells are just responding, right? And then when does this signal from these cells actually turn into something that I can think of as a face of the person sitting in front of me?
Yeah, so this is a long journey, I guess, that then this light information takes. So first, in the retina already, there is some processing that is done where, for example, you have other cells in this layer, like the retinal ganglion cells. They are sensitive to, for example, to certain orientations in space. There are some very cool experiments in neuroscience where they would show an animal different bars at different orientations, and then measure the response of the neurons. And for a neuron, when there was the bar that was exactly this orientation that it was the most sensitive to, it would respond a lot. So then you imagine combining the input from different cells. So I know now there is an edge on this orientation, and here there is another bar with this orientation. Then I can start forming a shape, right?
Does that mean that one cell is responding to like a 45-degree oriented object?
Yes, exactly. Diagonal, some more horizontal or vertical. And like this, there are cells for everything. There's also cells for color, for example, that are more responding to certain colors. And this is how the color information or the light information from the different cones gets compared. Also cells that respond both to color and spatial orientation or spatial detail. So this is how we start combining all this different information to try to form an image.
Cool. And so we know that not everyone sees colors in the same way, right? So there's also species that don't see colors, but there's also humans that are colorblind. So what happens to these people?
So mostly this is color blindness. It's mostly caused by some type of defect with the photoreceptors, and it's genetic usually. And also men are more likely to have it because it's a recessive gene associated to the X chromosome. So what can happen often, for example, is that people are missing one type of photoreceptor. So in that case, these comparisons that we were talking about are not able to take place because one of the inputs is missing. So they tend to lack the ability to see colors in one of the two channels we talk about. So for example, red and green is often one of the ones that are missing. So if you miss either red or the green cones, then you cannot distinguish red and green colors from each other very well.
Okay. So maybe to wrap it up, at the beginning, we were also talking about energy and light intensity. And I think it would be also maybe good to describe, when we talk about dim light and bright light, what it actually mean in terms of light. How do we measure this in science?
Yeah, so I guess I was talking in the beginning about, intensity. And the way we often measure this is with how it affects the visual system. So when we talk, for example, about lux, this is a measure that is only relevant to the human eye. If you were to measure it for another animal, you would have to come up with a different measure, unless they have exactly the same photoreceptors that we have.